Happy Wednesday, everybody. I know you've got a short day today, so I want to try to be cautious of our time here. Just to review what we talked about last time, we are in section 7.5. So chapter 7 is our integration techniques, and we are talking about our last technique, partial fractions. Now again, the thing that you're looking for this technique is we're looking for a polynomial over a polynomial in our integrand, right? And when we see that, we have a four-step process that we do here. The first one is we look at the degree of the top, and we check and see if the degree of the top is bigger than or equal to the degree of the bottom. In other words, is the highest power of x on the top bigger than or equal to the highest power of x on the bottom? If it is, we do long division? If it's not, you can just skip this step and move on to the next one. Okay? And we've seen long division before polynomials. I'm not going to get into that. What we then do is we factor the bottom of the fraction, and then based on that factoring, we find the partial fraction decomposition. Okay, and we call that PFD. Right? And we looked at several examples of that last time. We'll look at that again. And once you get that decomposition and you find those coefficients, then all you're left with doing is integrating. All right? Now, one of the types of problems that you may see on an exam or potentially a quiz, like maybe the quiz tomorrow, is I could just give you a fraction with the denominator factored, and I could ask, what's the form of the partial fraction decomposition? But don't solve for the coefficients. So let me give you an example here. So I could say something like, let's suppose we have x times x squared plus 1 times x plus 1 cubed. What is the form of the partial fraction decomposition here, but don't solve for the coefficients? That could be a quiz problem or an exam problem. What I would want you to do is notice that, so the x term is alone, so I would write that as a over x. This x squared plus 1 cannot be factored any farther, so I'm going to write that as bx plus c over x squared plus 1. And then this x plus 1 term, there's three of them, so I'm going to have a d over x plus 1, an e over x plus 1 squared, and an f over x plus 1 cubed. Okay? Make sense? All right. So let's try, based on this, what I talked about these terms, we call these irreducible quadratics. They can't be factored any farther. But we haven't done any example problems where you have an irreducible quadratic. So I am going to put, we're just going to do two examples here. And that will be it for today, again, because we've got a shortened time period. And these problems, when you get quadratics in there, the number of coefficients can get larger, as you can imagine. So let's try, we're just going to do two examples here. Let's do x squared minus 1 over x cubed plus x. So again, first thing I noticed that I've got a polynomial over a polynomial. That means partial fractions is a possibility, but I don't automatically do it. I say, first of all, is there a way to simplify? There really isn't. Is something in here the derivative of something else? So then I could use substitution. I can't. I definitely don't want to do integration by parts. There's no trig functions in here, and I don't see any square roots of 1 minus x squared or 1 plus x squared or x squared minus 1, so I don't do trig substitution, so I'm left with really just doing partial fractions here. So the first thing I do with partial fractions is I look at the degree of the top and the degree of the bottom, and I notice the degree of the top, 2, is smaller than the degree of the bottom, 3, so I don't need to do long division. I'm relieved of that here. So then I factor the bottom. Don't factor the top though. You do not need to factor the top. Okay, and this x squared plus 1 term does not factor any further. So what I'm going to do now is figure out the partial fraction decomposition here. So for the x term, I'm just going to have a over x. And for the x squared plus 1 term, I'm going to have bx plus c over x squared plus 1. We're good so far? Now I just need to figure out a, b, and c, and then we'll work on integrating this. So let's, just like we've done in the past, let's multiply through by the denominator here, x times x squared plus 1. So on the left side, the denominator goes away, and I just get x squared minus 1. A over x times this thing, the x's are going to go away, and I'm just going to have x squared plus 1. Bx plus c, the denominator x squared plus 1 goes away, and I'm just left with x. So one thing that immediately occurs to me is if I plug in x equals 0, you'll notice that this right term will go away completely. So let's go ahead and do that. So when x is 0, I get negative 1 equals a times 1 plus this whole thing is 0. So that means that a is negative 1. Well, that's helpful. Other thing now that you'll notice is that there isn't anything else clever that I can plug in that will cause everything except one thing to go away. So let's just plug in a couple of other things and see what happens. Let's try x equals 1, because I want to keep things simple here. So if I plug in 1 here, I get 0. Here I get a times 2. Well, I know what a is. A is actually negative 1. So I get negative 1 times 2. Stick that in here. Negative 1 times 2 plus x is 1, so I get b plus c times 1. So in other words, b plus c is 2. All right? Let's plug in x equals negative 1 now. If I do that, I again get 0 here. Negative 1 times negative 1 squared is 1 plus 1 is 2. So again, I get negative 1 times 2. Plus, and now I get, when x is negative 1, I get negative b plus c times negative 1. So in other words, if I put that 2 again on the other side, negative 1 times negative b is b minus c is 2. Okay, now we have to kind of harken back to your algebra days and think through if I've got that b plus c is 2 and b minus c is 2. Well, what you probably used to do would be, for instance, to add these two equations together. And I get 2b, c minus c is just 0, equals 4. So b is 2. Remember solving simultaneous equations? And if b is 2, you can see that c is going to have to be 0. So b is 2 here, and c is 0 here. Got it? And everybody follow? All right. So now what we're going to do is this integral now turns into this much simpler form, negative 1 over x, since a was negative 1, And b is 2, so I've got 2x plus 0, c is 0, over x squared plus 1. All right. Now the way that I'm going to do these two integrals is very different, so I'm going to separate them. We can actually just go ahead and do the first one. But I'm going to leave the second one like this. And I want you to take a look at that integral. I want you to turn to the person next to you and talk through how would you do it. Now it is a polynomial over a polynomial, but we've already done partial fractions, so you're not going to be able to make that look any better. So you're either going to have to simplify or you're going to have to do a substitution. Those are really your only two other options. You can't do integration by parts. There's no trig functions here, and there's no trig integrals. There's no trig substitution there. So do you do simplify or substitution, and if so, what do you do? Take a second and talk to somebody next to you. What you should be saying is you want to do a substitution here. U equals x squared plus 1, and the reason is that du is 2x dx. That top part is the derivative of the bottom part. Okay, so if I do that here, first part comes along for the ride, and I've got 1 over u times du. So in other words, I have natural log of absolute value of u. Okay, now don't get so excited that you did all this work and you're done, there's no integrals. You need to make sure that you plug x's back in. So your final answer has to be with x's. If you started with x's, then you have to end with x's. Okay? And that's it. Okay, one other note I want to make here is that if this term had happened to not be 0, so in other words, if this happened to be, it wasn't, but if it happened to be -3, and so you happen to have a -3 there, you would actually have to separate these integrals and do them very differently. You would have to have the integral of 2x over x squared plus 1 minus the integral of 3 over x squared plus 1. Okay. I'm not sure if you can see this. This one we would do like we normally just did. We would do a substitution. But this one, right here, x squared plus 1 on the bottom, here you would actually you could do one of two things. You could recognize that it's an arctangent, or you can do a substitution, x equals tangent theta. So dx is secant squared theta d theta. And if you did that, you would have to plug back in, do some cancellation, and then redo the triangle again. So the only thing I'm pointing out here is, number one, you would have to split this integral into two different integrals that you treat very differently. And number two, you can see that our trig substitution ends up coming up here, which is why this technique is listed after trig substitution, because sometimes you may end up having to go back up to trig substitution. All right? Let's look at one more example, and that'll be it for today. Then you'll have some more time to work on your homework. Now, if you're not able to get that homework done fully by the end of today, I understand that. You can hold on to it and work on it a little bit more, and then try to turn it in tomorrow. All right? Okay, last example today is x squared minus x plus 9 over x squared plus 9 quantity squared. Okay. Again, polynomial over a polynomial. There's no way to mentally go down that list that I had. There's no way to simplify it. for substitution, I do have a composition here. If I let u equal x squared plus 9, there is no du up here. So that's not going to work. No, I don't want to do integration by parts. No trig functions and no clear trig substitution. That may come later. So I'm left doing integration, doing partial fractions. Next step that I would do is I would look at the degree of the top and the degree of the bottom. Now technically, the bottom's already factored, so don't get confused by this. If the bottom were multiplied out, I just want to show this to you here. X squared plus 9 times x squared plus 9 would give you x to the 4th plus 18x squared plus 81. Notice the degree of the bottom is actually x to the 4th, not x squared. Okay? So the point here is that the degree of the top, 2, is less than the degree of the bottom, 4. So we're good to go here. Then what I would do is factor the bottom, so we're kind of back here, and write out my partial fraction decomposition. So let's go ahead and do that. Now x squared plus 9 does not factor any farther. So what I would do, because I've got this term repeated, is I would write it as ax plus b over x squared plus 9, and then cx plus d over x squared plus 9 quantity squared. Okay? We're good to go. Okay. Let's multiply through now by x squared plus 9 quantity squared. And that gets rid of the denominator here, so I just have x squared minus x plus 9 equals, over here I get ax plus b times one of those x squared plus 9s. And then the denominator here cancels and I just get cx plus d with nothing else on there. All right. Everything clear so far? All right. Now there's a few different ways that I can solve this. I can plug in, and the only point here that I could plug in that would be nice would be x equals 0. So before I do that, I want to show you a different technique that you can use here. Now you can use either of these techniques to find these coefficients. But this is another technique that you can use. So I'll just again write the left side, x squared minus x plus 9. Let's multiply out the right side. So if I multiply it out, I've got ax cubed. So I'm going to FOIL it. So then I've got my outer, which is 9. Let's do the inner first. Plus bx squared plus 9ax plus 9b. Okay, I just multiply these out. And then what's left over is cx plus d. So let's combine a couple terms here. This is my x cubed term. This is my x squared term. My x term is actually these two. So it's really 9a plus c times x. And then my constant term is these two terms here, 9b plus d. Okay. Now here's how this other technique works for finding a, b, c, and d. And depending on the context, this one works better. Sometimes the other technique that I showed you works better. This, on the left side, this is a polynomial. On the right side, this is also a polynomial. And these two polynomials are always equal. They're always equal. So that means that if I have an x cubed term on this side, that should equal the x cubed term on this side. Now the x cubed term on this side is actually 0x cubed, right? Right, there's no x cubed term over here. So what does that tell you about a? A actually has to be 0, right? The x cubed term on this side and the x cubed term on this side actually have to equal each other. So that means that a has to be 0. Well, that's super nice, because that means that this term's also 0. Okay? Well, that's good. Now compare, here's the x squared term on this side, and here's the x squared term on this side. What does that tell you about b? B has to be 1, right? Do you see that? B actually has to be 1, because the x squared term here and the x squared term here have to equal each other. So B is actually 1 here, so that makes that 9. So A is 0, B is 1. Now, can you figure out C? Okay, the x term on this side is negative x. The x term on this side is cx. So what does that tell you C has to equal? C is going to have to equal negative 1. And now, the constant term on the left side is 9, and the constant term over here is 9 plus d. So what does that tell you? D has to equal 0. So what's actually happening here, the A term is 0, the B term is 1, the C term is negative 1, and the D term is 0. So in other words, you follow that? I was just comparing the two polynomials, and that let me read off A, B, C, and D. So in other words now, this crazy thing, in other words this, actually equals 1 over x squared plus 9 minus, or plus, let me just leave it as plus for right now, negative x plus 0 over x squared plus 9 quantity squared. Okay? So now supposedly that should be a lot easier for me to integrate than what I had before. So let's split these, because I'm actually going to do them in two different ways. So I'm going to split it as 1 over x squared plus 9 minus x over x squared plus 9 quantity squared. I want you to turn to the person next to you and just talk to them briefly. How would you do this problem? And how would you do this problem? The way that you do the two of them is very different. So just take a minute, talk to the person next to you. How would you do each of those integrals? Okay, let's take the easier one first. This one's actually the easier one. This one, you should see a composition here. So thinking through your techniques, you've got a composition. The inside, the top is basically the derivative of the bottom, or the inside of the bottom. So for this one, I'm going to let u equal x squared plus 9, and du is going to be 2x dx. And so 1/2 du is x dx. Okay, so that's actually going to let me do that one, and that's going to be a much easier integral to do there. With this one, it's kind of, it should remind you of arctangent, 1 over x squared plus 1, but I've got x squared plus 9. So what I'm going to do here, I'm going to do a trig substitution, And I'm going to let x equal 3 tangent theta, because when I square it, I'm going to get 9 tangent squared plus 9, and I can factor that 9 out. Okay? So x equals 3 tangent theta. This reminds me of x squared plus 1, except it's x squared plus 9. Dx is 3 secant squared theta d theta. Okay, so let's try each of those two integrals now. So for this first one, I've got 1 over x squared is now 9 tangent squared theta plus 9. And the dx is 3 secant squared theta d theta. Right? Minus, this integral becomes, the bottom is just u squared, and the top is 1/2 du. So that second one is definitely something that I can do. This is just u to the minus 2, and I'm going to be able to integrate that. So now on this first one, let's factor out the 3 and the 9. So we'll pull out the 3 and the 9. And on the bottom, I've got tangent squared plus 1. And on the top, I've got secant squared. Well, tangent squared plus 1 is secant squared. And so that secant squared cancels this secant squared. We'll come back to that in a second. This integral is just u to the minus 2. So 3 over 9 is 1/3, and I've got the integral of d theta. And when I do this other integral, it's just u to the minus 1 over minus 1. The integral of d theta is just theta. So I've got 1/3 theta plus 1 over 2u plus c. And now all I've got to do is go back to my original, everything has to now be in x's. So for the theta part, you'll notice that tangent theta is x over 3, so theta is arctangent of x over 3. So that's that part. Plus 1 over 2, and u is x squared plus 9, plus my c. There you go. It's a lot of work, but we were able to do it. And before, we didn't have any techniques that we could use to actually be able to do that. So that is it. If you've got a little time, feel free to keep working. Otherwise, you can, if you don't have that homework that's due today done, you can save that and work on that for next time. The quiz tomorrow is going to be over trig substitution. I may put a trig integral in there and partial fraction. So I could give you a partial fraction decomposition, say write this out but don't solve for the coefficients. I could give you a simple partial fraction decomposition. I'm not going to give you a quadratic on the quiz tomorrow because you haven't done homework on that yet. Okay? So we'll have a quiz tomorrow, and then we'll review for the Chapter 7 exam along with Section 510 on hyperbolic trig functions. All right? See you tomorrow. Have a great day.